What if an AI could do more than just spot patterns in data? What if it could actually learn the fundamental laws of physics? Well, today we're going to dive into how that exact idea is being used to solve a problem that's literally underground, but is absolutely critical to the safety of some of our most massive structures.
So, what's the big challenge we're talking about? It all comes down to the hidden path of water as it seeps through soil and rock. Now, this isn't just about, some damp ground. For engineers, this invisible flow is a major concern.
I mean, think about it. When you build something as massive as a dam, you have to know where that water pressure is going. Unseen seepage can literally undermine the entire foundation, threatening the stability of the whole structure. So predicting this invisible flow isn't just important, it is absolutely essential for safety.
So how in the world do you map something you can't even see? Well, for decades, engineers have had a way, a very powerful, but also incredibly demanding computational method.
Yeah, they've been solving it piece by tiny piece, using a technique that's known as the finite element method. At its heart, the idea behind FEM is pretty clever. It works by taking a massive, complex area, like all the ground under a dam, and breaking it down into thousands and thousands of simple, manageable little pieces that a computer can actually analyze.
This grid that you're looking at here is called a mesh, and it is the foundation for the entire analysis. But creating this digital mosaic, wow, it is a painstaking, incredibly time-consuming process that requires some serious expertise.
And this is where the problems start to creep in. Creating a good mesh is tough, and it gets way harder with complex shapes. The accuracy of your entire calculation hinges on the quality of this mesh. And what about problems where a boundary, like the water table, is constantly shifting? Oh man, that is a huge headache for this method.
And this right here, this is the question that changes everything. What if you could get the right answer without having to build that ridiculously complex digital mosaic in the first place?
And the answer brings us to the breakthrough at the heart of this research. A very special kind of AI called a physics-informed neural network, or, as you'll hear me call it, a PIN.
Now, a PIN isn't just any AI. Its defining feature, the thing that makes it so cool, is that it doesn't just learn from data. It's also taught the fundamental laws of physics that govern the problem it's trying to solve.
I absolutely love this analogy because it makes the difference so crystal clear. A standard AI is like that student who only crams by looking at old exam answers. Sure, it can spot patterns, but it has no idea why they're correct. The PIN, on the other hand, is the student who actually read the textbook. It knows the underlying formulas, so its answers have to make physical sense.
Okay, so how does it actually do this? Well, the magic is in something called the loss function. Think of it like a built-in physics tutor. Every single time the AI guesses an answer, this tutor checks it against the known physical laws. If the answer breaks a rule, if it's physically impossible, the AI gets penalized. This process forces the network, over and over, to find solutions that don't just fit the data, but also obey the laws of physics.
So the researchers put this new AI to the test. They set up a head-to-head challenge against the classic finite element method. So, how did it stack up? Let's take a look at the results.
For their first benchmark, they picked a true classic, calculating the water pressure in the foundation right underneath a concrete gravity dam. It's a perfect real-world test.
And at first glance, both methods seem to produce a very similar result. These heat maps show the hydraulic head, which is basically the water pressure, and they look almost identical. But looks can be deceiving, right? The real story isn't in the picture, it's hiding in the numbers.
And here it is. This is the moment of truth. When compared to the known correct solution, the classic FEM had a relative error of 3.82%. The PIN, however, was significantly more accurate, with an error of just 1.38%. It didn't just get an answer that looked right, it got one that was more precise. All right, so for the next round, they really turned up the heat. They tested a free surface problem, where one of the boundaries, like the water table, isn't known beforehand. This is exactly the kind of tricky scenario that gives those mesh-based methods so much trouble.
Get this, in this much harder test, the PIN's predictions, when compared to actual experimental data, had an average relative error of only 1.24%. I mean, that is just incredibly accurate for such a complex problem.
So what about the traditional method? Well, the finite element method came in with an error of 2.53%.
So, in the more challenging test case, the pin was roughly twice as accurate as the established standard. That's a huge win.
So what does all this really mean for the future of engineering analysis? Let's take a look at the study's key conclusions.
And here it is, straight from the researchers themselves. They stated unequivocally, for these critical seepage problems, the physics-informed neural network doesn't just match the finite element method, it actually surpasses it in accuracy. So let's just recap the big picture here. What we have is an AI that brilliantly merges machine learning with fundamental physics. It gets rid of that tedious, time-sucking mesh generation step, it delivers superior accuracy, and it proves itself to be a powerful and precise new tool for tackling these absolutely critical engineering problems.
And you know, that leaves us with a fascinating and kind of mind-blowing thought. We've just seen an AI learn the physics of how water flows through the ground. This same approach could be applied to heat transfer, to structural mechanics, to electromagnetism. So what invisible forces and complex physical laws will an AI master next?